The Earth's atmosphere is composed of several gases. Most abundant gas in the Earth's atmosphere is nitrogen, which accounts for about 78% of the mass of dry air. Molecular nitrogen in the atmosphere cannot be used directly by either plants or animals and needs to be converted into nitrogen compounds. Plants absorb nitrogen from the soil in the form of nitrate and ammonia. Ammonium nitrate, ammonium chloride, ammonium phosphate, sodium nitrate, nitric acid, ammonium sulphates are some important nitrogen compounds. Ammonia is the main raw material used in the manufacture of chemical fertilizers. Take some ammonium chloride in a test tube and heat it. We can sense a peculiar smell. When we introduce a wet red litmus paper into the gas, the color of the litmus paper will turn to blue. From this, we can understand that the evolving gas is ammonia and it has basic nature. When ammonium chloride is heated, it undergoes thermal dissociation to form ammonia and hydrogen chloride. NH4Cl gives NH3 plus HCl. Let us say the preparation of ammonia in laboratory. Ammonia is prepared in the laboratory by heating a mixture of ammonium chloride and calcium hydroxide. They both react together to form calcium chloride, water, and ammonia. CaOH twice on reaction with 2NH4Cl gives CaCl2 and 2NH3 and 2H2O. Ammonia gas is passed through fresh quicklime to effectively dry it. Ammonia is collected by upward delivery as it is lighter than air. Some substances can absorb moisture to make materials dry. They are known as drying agents. Quicklime, silica gel, concentrated sulfuric acid, etc. are used for this in appropriate instances. Collect ammonia gas in a round-bottom flask. Close the flask with a cork containing a jet tube and an injection syringe. Using the syringe, introduce a few drops of water into the flask. Close the mouth of the jet tube with your finger and shake the flask well. Dip the end of the jet tube in water containing some phenolphthalein in a beaker. We can see that water rises into the flask and forms a pink color fountain. As the gas dissolves, a partial vacuum forms inside the flask. The external air pressure will force water up the tube and through the jet, forming a fountain. The ammonia gas dissolves in water emerging from the gel, and phenolphthalein changes the color of the solution collected in the flask. NH3 on reaction with H2O gives NH4OH. Reversible reaction and irreversible reaction. Reactions which take place simultaneously in both the direction under the same set of conditions are called reversible reactions. For example, ammonium chloride is a white solid that breaks down into ammonia and hydrogen chloride gases when heated. Then this reaction is reversed and ammonia and hydrogen chloride gases react to form ammonium chloride again. NH4Cl reversibly forms NH3 and HCl. In reversible reactions, the reaction in which the reactants are converted into the products is called the forward reaction, and that in which the products are converted back into reactants is called backward reaction. See more examples of reversible reactions. Nitrogen combines with oxygen to form nitric oxide. N2 plus O2 reversibly forms 2NO. Calcium carbonate gets converted into calcium oxide and carbon dioxide. CaCO3 reversibly forms CaO and CO2. Chemical changes in which the reactants react to form products, and under the same condition the products are not converted to the reactants, are called irreversible reaction. Zinc reacts with hydrochloric acid to form zinc chloride and hydrogen. Zn, on reaction with 2HCl, gives ZnCl2 and H2. Sodium reacts with water to form sodium hydroxide and hydrogen. 2Na, on reaction with 2H2O, gives 2NaOH and H2. Industrial production of ammonia. Ammonia is produced on a large scale by the reaction between nitrogen and hydrogen under high pressure and optimum temperature in the presence of a suitable catalyst. This method is known as Haber process. Hydrogen is obtained by reacting methane with steam or through the cracking of oil, and nitrogen by fractional distillation of air. The mixture of nitrogen and hydrogen going into the reactor is in the ratio of 1:3. The gases are pressurized to about 150 to 300 atm inside the compressor. The pressurized gas is pumped into a tank containing beds of iron catalyst. 450 to 500 degrees Celsius is a compromise temperature, producing a reasonably high proportion of ammonia. In these conditions, hydrogen and nitrogen will react to form ammonia. When the gases leave the reactor, they are hot and at a very high pressure. Ammonia is easily liquefied under pressure as long as it's not too hot, and so the temperature of the mixture is lowered enough. For the ammonia to turn into a liquid. The nitrogen and hydrogen remain as gases even under these high pressure and can be recycled. N2, on reaction with 3H2, reversibly forms 2NH3 and heat. The state at which the rate of backward reaction equals the forward reaction is called equilibrium state. Reversible reactions do not stop itself. These chemical reactions take place in both directions. At a particular temperature, the reactants and products reach at an equilibrium state. The following changes get unseen. The changes in concentration, temperature, and pressure influence the equilibrium state. The result of the changes due to the change in these factors was predicted by a scientist named Chatelier. Chatelier's principle. If a change in concentration, pressure, or temperature is brought about in a system at equilibrium, system will readjust by itself so as to cancel the effect of the change, thus attaining a new equilibrium state. This is Le Chatelier's principle. Let us see how the Le Chatelier principle is applied to the commercial production of ammonia. Influence of concentration. During the synthesis of ammonia, if we increase the concentration of any one of the reactants in the equilibrium state, the rate of forward reaction increases and more amount of ammonia is formed. Influence of pressure. Look into the reaction in which nitrogen and hydrogen react together to form ammonia. N2 on reaction with 3H2 reversibly forms 2NH3. In this chemical reaction, 1 mole of nitrogen combined with 3 mole of hydrogen to give 2 mole of ammonia. As a result of this reaction, the volume decreases. But when ammonia decomposes to nitrogen and hydrogen, the volume increases. That means when pressure is increased, according to Le Chatelier's principle, nitrogen and hydrogen react to give more ammonia. Chemical equilibrium and temperature. In a reversible reaction, if one is exothermic, then another reaction will be endothermic in nature. Generally, ammonia-forming reaction is exothermic reaction. If temperature increases, the system tends to decrease it. As a result, the forward reaction is more favorable, resulting in the formation of ammonia. Sulfuric acid. Sulfuric acid is known as the king of chemicals. It is one of the most important industrial chemicals. Its greatest use is in the production of fertilizers, but it is also used in the refining of petroleum and production of automobile batteries, explosives, pigments, iron and other metals, and paper pulp, etc. Let us see the industrial preparation of sulfuric acid. Nowadays, sulfuric acid is prepared by contact process all over the world. When sulfur is burned, it produces sulfur dioxide gas. S on reaction with O2 gives SO2. The main step is the oxidation of sulfur dioxide. This takes place at a favorable temperature of 450 degrees Celsius to 500 degrees Celsius. At low temperature, rate of reaction decreases. To increase the rate of reaction, a catalyst, vanadium pentoxide, is used. Optimum pressure is about 1 to 2 atm. When sulfur dioxide is oxidized, we get sulfur trioxide and heat. 2SO2 on reaction with O2 forms 2SO3 and heat. Sulfuric acid can be obtained by dissolving sulfur trioxide in water. But since the dissolution of sulfur trioxide in water is highly exothermic, the sulfuric acid that is formed first vaporizes to form a smog which hinders further dissolution. Hence, this method is not used for the preparation of sulfuric acid. Instead, sulfur trioxide is dissolved in 98% sulfuric acid solution, get oleum. SO3 on reaction with H2SO4 forms H2S2O7, that is oleum. And sulfuric acid of any concentration can be prepared by adding required quantity of water to oleum. H2S2O7 on reaction with H2O gives 2H2SO4. The reaction between acid and water is exothermic reaction. Hence, when concentrated acids are diluted, slowly add the required quantity of acid in a thin stream to water with continuous stirring. Never add water into concentrated acid. When you add concentrated sulfuric acid to sugar, the result is interesting. The sulfuric acid dehydrates the carbohydrate sugar, removing the water and heating it into steam, leaving behind a carbon form. Take a small amount of blue vitriol in a watch glass and add a few drops of concentrated sulfuric acid to it. As concentrated sulfuric acid absorbs the water of crystallization from blue crystalline copper sulfate, it is converted to white anhydrous copper sulfate. Hence, the process of removing the chemically combined water from substances is called dehydration. The substances that remove water from the chemicals are called drying agents. Concentrated sulfuric acid is used for drying gases like sulfur dioxide and hydrogen chloride during their laboratory preparation. Let us see the reaction of sulfuric acid with salts. Take some dilute sulfuric acid in a test tube. Add a little sodium carbonate to it. We can see that the sulfuric acid combines with carbonate salts and forms carbon dioxide gas. Pass the gas produced through clear lime water taken in another test tube. Carbon dioxide passed into lime water gives a milky solution. Nitric acid forms sulfuric acid on reaction with nitrate salts, and it forms hydrochloric acid on reaction with chloride salts. For example, sodium nitrate reacts with sulfuric acid to form nitric acid. NaNO3 on reaction with H2SO4 gives NaHSO4 and HNO3. Similarly, sodium chloride reacts with sulfuric acid to form hydrochloric acid. NaCl on reaction with H2SO4 gives NaHSO4 and HCl. Test to detect sulphates. Take a small quantity of aqueous solution of sodium sulfate in a test tube. Add 3 or 4 drops of barium chloride solution into it. When a solution of barium chloride is poured into the solution of sodium sulfate, a white precipitate of barium sulfate is formed. Na2SO4 on reaction with BaCl2 gives BaSO4 and 2NaCl. Barium carbonate also forms a white precipitate. To confirm the presence of sulfate, it is to be tested by adding concentrated hydrochloric acid to it. Barium sulfate is insoluble in hydrochloric acid. Test to detect chlorides. Take a small quantity of sodium chloride solution in a test tube. Add a few drops of silver nitrate solution into it. A white curdy precipitate is formed. If the white precipitate dissolves on adding ammonium hydroxide, it can be confirmed that the given salt is chloride salt. NaCl on reaction with AgNO3 gives AgCl and NaNO3. Test to detect nitrates. Take a small quantity of aqueous solution of nitrate in a test tube. Add an equal volume of freshly prepared ferrous sulfate solution to it. Shake well. Then pour concentrated sulfuric acid through the sides of the test tube slowly without shaking it. Formation of a brown ring at junction where the two solutions meet indicates the presence of nitrate. Now we are familiar with the methods of preparation and the general characteristics of industrially important compounds like ammonia and sulfuric acid.